All right, so you know Richard Feynman, right? The iconic
Oh,
physicist.
yeah, definitely.
Yeah, you probably picture him playing the bongos or like cracking safes at Los Alamos.
Huh.
But here's something that might surprise you.
Okay.
Way back in the early 1980s, like long before AI was the the hot topic it is now,
Yeah.
Feynman was already diving deep into neural networks and machine learning.
Wow. Yes.
For today's deep dive, we're going to uncover this like kind of hidden chapter of Feynman's intellectual journey.
I'm really fascinated by this.
Yeah.
It's not just some like passing interest that he had.
Right.
The sources we've got like point to a really deep engagement with this stuff.
Yeah.
It's this whole other side of Feynman's like, endless curiosity
Mm-hmm.
that often gets overshadowed by his like, his huge contributions to quantum physics. He wasn't just like observing this from a distance or anything.
Right.
He was right in the thick of it.
Absolutely. And like you got to picture the like intellectual energy at Caltech back then.
Oh, yeah.
You've got John Hopfield who had just arrived and was really driving the like resurgence of neural networks.
Mm-hmm.
And then you've got Carver Mead, a pioneer in VLSI design.
Oh, wow.
Very large scale integration.
Yeah.
Think of him as like the guy who saw how to like build brain-like computation into hardware to make it super fast.
Huh.
And these are the folks that Feynman was like, hanging out with and bouncing ideas off of.
Yeah, and to really understand Feynman's perspective here,
Yeah.
it's super important to remember like what the the dominant approach to AI was at the time,
Mm-hmm.
which was symbolic AI.
Right.
This is all about rules and logic
Yeah.
that you like program directly into computers.
Mm-hmm.
But Feynman, always wanted to see things differently.
Yeah.
He was really drawn to the potential of neural networks to like tackle those tasks that symbolic AI just really struggled with.
Right.
Especially things like pattern recognition and learning from data.
Yeah.
Much more like how a human brain actually works.
Yeah. Right. So for today's deep dive into this, we're going to unpack Feynman's early exploration of AI through this lens of neural networks.
I'm excited.
What were his big ideas?
Yeah.
What problems was he like trying to solve?
Yeah.
And maybe most interesting is how do his insights from like 40 years ago hold up against the amazing progress we've seen in AI and machine learning in the decades since then?
Yeah, that's the big question.
Okay, so let's dive in.
Let's do it.
What was it that like initially sparked his interest in this area?
Well, our source material like really points to this like core belief that Feynman had.
Okay.
That neural networks offered a way to break free from those limitations of the symbolic AI approach.
Okay.
He saw this like, immense potential in getting machines to like learn from experience,
Mm-hmm.
to recognize patterns in a way that's like, flexible and adaptable rather than just blindly following pre-programmed rules.
Okay.
And this whole idea of machine learning was like super central to his thinking even back then.
And it wasn't just a theoretical interest for him.
No, not at all.
Right. He was actually in the trenches.
Yeah.
He participated in the physics of computation course with Hopfield and Mead,
That's right.
which signals like a real commitment to getting into the nitty-gritty of this new field.
Yeah, definitely.
Yeah.
What do you think? Totally. And what's really interesting is that Feynman, like true to form, seemed to be approaching this whole thing from first principles.
Oh, yeah.
He had this uncanny ability to like rederive things himself to get to the essence of a problem.
Right.
And it's quite plausible that he was independently rediscovering some of those core concepts of neural networks.
Oh, that's so Feynman.
Totally.
But it is fascinating to think about the historical context here,
Yeah.
because research into neural networks has had its its ups and downs.
Oh, for sure.
It hasn't been a straight line to success.
Right.
Remind us a little bit about that.
Yeah, so there was this initial wave of excitement about neural nets back in the late 50s and early 60s.
Okay.
But then that enthusiasm kind of fizzled out.
Yeah. Yeah.
And a big part of that was the book Perceptrons by Minsky and Papert,
Right.
which really highlighted some of the limitations of those simpler early neural network models.
Okay.
And that book had a huge impact. It really dampened the whole field
Mm-hmm.
and led to a drop in both research and funding.
So like the early 80s were kind of a revival period,
Exactly.
a second coming of neural networks.
Yeah, a second wave of interest.
Okay.
And Feynman was right there in the middle of it.
Okay.
Key figures like Hopfield Hinton and Sosnowski were like instrumental in this resurgence.
Okay.
They brought in all these new mathematical tools, more sophisticated algorithms, and different ways of structuring these networks.
Right.
And that really breathed new life into the whole field.
And you mentioned that physicists in particular were drawn to this way of thinking.
Yeah.
Why was that connection so strong?
Well, if you think about it,
Yeah.
neural networks have this inherent physics-like quality
Okay.
at a certain level of abstraction anyway.
Right.
A lot of the core models could be described using equations,
Okay.
much like the systems that physicists study all the time.
Okay.
This mathematical language really resonated with people like Feynman,
Right.
who were accustomed to thinking in terms of energy and dynamics and interactions.
So it's like they were speaking the same fundamental language.
Exactly.
Okay.
Even if the specific terms were a little different.
Yeah, even with this, interest in neural networks.
Yeah.
Feynman also had connections to the symbolic AI folks.
Oh, that's right.
Right. It wasn't like he was totally in one camp or the other.
Yeah, he was open to different ideas.
Right. He was exploring multiple paths to AI.
Yeah, and his friendship with Marvin Minsky is well documented.
Right. One of the giants of symbolic AI up at MIT.
Absolutely.
And this led to a very interesting interaction with Gerald Sussman, who was one of Minsky's former students.
Yeah.
Tell us about that, because it really highlights these contrasting viewpoints at the time.
So to set the stage for you, we've got this really interesting intellectual clash happening.
Okay.
Minsky, representing that established symbolic perspective.
Right.
He actually helped arrange for Sussman to go on sabbatical to Caltech.
Oh, wow.
The idea was for Sussman to really engage with Feynman on this whole AI thing,
Okay.
bringing that symbolic viewpoint into the mix,
Okay.
while also pursuing his own work on a planetary orbit computer.
So we've got these two completely different approaches to AI being discussed and debated.
Brother right there in the Caltech lunchroom.
I love that image.
Yeah, it must have been fascinating.
And it sounds like Sussman was pretty skeptical of Feynman's interest in these neural networks.
He was.
Oh.
Sussman was so deeply rooted in the principles of symbolic AI
Right.
that he saw Feynman's ideas about neural networks as kind of simplistic.
Oh, really?
Yeah, maybe even echoing those earlier attempts that hadn't really gone anywhere.
Right.
And you also got to remember that symbolic AI itself was starting to hit some roadblocks.
Oh, right. Some problems.
Yeah, starting to enter that period that people call the AI winter.
Oh, right.
So there was this sense of, maybe this whole approach is running out of steam.
And how did Feynman respond to that skepticism?
Well, this gets to a really interesting point
Okay.
about the nature of expertise.
Okay.
Feynman felt that Sussman knew too much
Oh, wow.
about the current state of AI research.
Too much knowledge can be a bad thing.
Yeah, in a way.
Okay.
Feynman's view was that all this deep knowledge that Sussman had might actually be blinding him
Oh, wow.
to the potential of this completely different neural network-based approach.
Okay.
Feynman often believed that, real breakthroughs come from challenging those existing assumptions.
Yeah, it's that classic tension between established wisdom and the disruptive new idea.
Absolutely.
Now, Feynman didn't just have these abstract thoughts about AI. He had a very specific dream project,
He did.
as it's described in our source material.
Yeah, what was at the heart of that vision?
Yeah, what was his vision?
So Feynman was really focused on this idea of nurturing artificial intelligence through neural networks.
Okay.
His ultimate goal was to train, shape, or perhaps even evolve a network to achieve real intelligence.
Okay.
And he even had this specific idea of a person-like and female learning machine.
Wow, that's a very striking image.
It is.
What was the thinking behind that specific vision of a female learning machine?
Well, the specifics are a bit sparse in the source material,
Okay.
but the central idea seems to be this. You have a machine that learns and acquires skills in a way that's analogous to how a human baby develops.
Oh, wow.
And scientists would act as these guides, carefully providing the right learning experiences at the right time,
Okay.
kind of shaping its development.
And what was Sussman's reaction to this?
Well, predictably, Sussman was not convinced.
Okay.
He thought the plan was naive.
Oh, wow.
He drew parallels to earlier AI concepts that hadn't really panned out,
Right.
which really highlights, how fundamentally different their views were on how to get to AI.
Okay, so Feynman was leaning into this neural network approach.
He was.
And he was doing it in a way that seemed very connected to his background in physics.
Absolutely.
The source mentions these physics-like neural networks.
Yeah.
What does that actually mean?
Oh, what's really insightful here
Yeah.
is that Feynman was drawing these direct analogies
Okay.
between neural networks and physical systems,
Okay.
especially using the framework of statistical mechanics,
Right.
which was like, his bread and butter.
He knew that stuff inside and out.
Oh, yeah.
Okay.
Like if you think about the strength of the connections between neurons,
Mm-hmm.
often denoted as T,
Okay.
you can think of those as being like the interaction strengths between atoms in a material.
Oh, okay.
There's a direct parallel there.
So he's looking at these networks through the lens of a physicist.
Exactly. Trying to identify the underlying principles that are like, mirroring the behavior of physical systems.
That makes sense.
Even Feynman's own variational method from statistical mechanics
Mm-hmm.
could be applied to understanding key properties of Hopfield's neural networks
Wow.
and the Boltzmann probability distribution,
Right.
which describes the likelihood of different energy states in a physical system.
Okay.
That also found a counterpart in these early neural models.
Okay, so there's this deep connection.
Yeah, but there's a crucial difference, though.
What's that?
These neural networks aren't just static systems.
Right. They're not like a fixed arrangement of atoms.
Exactly.
Okay.
The connection strengths in a neural network, they can change. They can adapt through learning,
Yeah.
unlike the fixed interactions you see in a lot of basic physical models.
Okay.
And this adaptability is what gives them the power to learn and evolve to
Right.
respond to data.
Okay. The source gets into some of the math here,
A little bit.
talking about mean field theory. Can you explain that in a way that's not going to, make everyone's eyes glaze over?
I can try.
What's the key takeaway for our listeners?
So mean field theory is basically a way to simplify our understanding of a complex system
Okay.
that has lots of interacting parts
Right.
by looking at like the average influence of all those parts
Okay.
on just one single component.
Okay, so like zoom in on one thing and see how the average of everything else is affecting it.
Yeah, exactly.
Okay.
And in neural networks, this helps us understand how the activation of one neuron
Right, whether it fires or not.
exactly
Okay.
is affected by like, the overall activity of all its neighbors
Okay.
on average.
Okay.
And this allows us to come up with equations that describe the network's behavior
Okay.
and its tendency to settle into stable patterns,
Okay.
or what we call fixed points.
Okay.
And this is where Hopfield's model comes in.
Right, with his analog neurons.
Yeah.
Where the activation levels can take on a range of values.
Right, not just 0 or 1. They could be like, 0.5 or 0.7 or whatever.
Okay, so how does mean field theory connect to his work?
So Hopfield used mean field theory
Okay.
to derive an equation that basically describes the stable states of a network
Oh.
that's made up of these analog neurons.
Okay.
And his model showed how the network could potentially solve problems by settling into these states of minimal energy.
Okay.
It's kind of like a physical system finding its lowest energy configuration.
Right.
It wants to be in that most stable, relaxed state.
I see. So the network is trying to find that lowest energy state.
Exactly.
Okay.
And that corresponds to a solution to a problem or a stored memory.
Okay, I'm with you.
And later on, these ideas were extended
Mm-hmm.
to networks with neurons that just have those two states, 0 or 1.
Okay.
Like a neuron's either firing or it's not.
Right.
And that led to the introduction of this thing called the sigmoid activation function,
Okay, I've heard of that.
which provides a smoother transition between those two states,
Okay.
making the models a little bit more biologically plausible.
Right.
So instead of this sharp on or off,
Yeah.
it's more of a gradual increase in activity.
So we've got these networks that can settle into these stable states.
Yeah.
But how do they actually learn?
Right. That's the big question.
The source talks about neural learning dynamics
Yeah.
and applying statistical mechanics to that.
Uh-huh. So here's the idea.
Okay.
We want to take that statistical mechanics framework
Mm-hmm.
and use it to describe how those connections between neurons
Right.
can actually change over time as the network learns.
Okay.
And so we draw these parallels to the dynamics of neuron activations.
Okay.
And we start to explore how to make those connection strengths,
Yeah.
that TK matrix we talked about,
Mm-hmm.
how to make those dynamic
Okay.
so they're not fixed anymore.
Right. So they can adjust based on the data that the network sees.
Exactly.
And that's what led to learning rules like Hebb's rule,
Yeah.
which is probably familiar to anyone who's dabbled in neural networks.
Neurons that fire together, wire together.
Exactly.
It's the basic idea.
Right.
And that found a mathematical expression within these statistical mechanics-inspired learning dynamics.
Okay.
So the strength of the connection between two neurons
Mm-hmm.
would increase if they were frequently active at the same time.
Okay.
And that way the network encodes the patterns that it's been exposed to.
Okay. I'm following you.
The source also explains how these concepts pave the way for feed-forward, multi-layered neural networks.
Right, or MLPs,
Yeah,
which are like, the foundation of so much of deep learning today.
they are.
So how did that evolution happen?
So by introducing some constraints on the network structure,
Okay.
like organizing neurons into distinct layers
Okay.
and only allowing connections between adjacent layers,
Mm-hmm.
and by carefully scaling those connection weights,
Okay.
you could essentially create a network where information flows in one direction,
Okay.
from input to output.
Okay.
And this architecture, the MLP, became super important because it could learn these complex relationships between inputs and outputs,
Okay.
like way better than those earlier models.
And the key technique for training these MLPs was backpropagation.
Yeah.
The source goes into some detail there.
It does.
What's the core idea behind backpropagation?
So at its heart, backpropagation is a sufficient method
Okay.
for figuring out how to use the error at the network's output
Mm-hmm.
to adjust the weights in all the layers before it. It uses calculus,
Of course.
the chain rule specifically,
Okay.
to send an error signal backwards through the network.
Okay, so it flows in reverse.
Exactly.
Okay.
And that lets you determine how much each connection contributed to the overall mistake.
Okay.
And then you can use that information to systematically tweak those connection weights
Right.
to improve the network's performance.
So it's like assigning blame or credit to the different connections.
Yeah. Kind of,
Okay.
based on how much they contributed to the error.
And this guides the learning process. Now, the source also mentions some challenges with
Yeah.
backpropagation when you try to train really deep networks.
Yeah.
Like sometimes the error signal can weaken or explode, and that led to all sorts of new techniques to stabilize the training process.
Exactly.
Okay, so let's zoom out a bit.
Okay.
The source talks about this period after the 1980s as the AML spring.
Right. This time of explosive progress.
Yeah.
Just huge advancements.
Looking back at Feynman's early work,
Yeah.
how do his initial ideas line up with this explosion of progress?
What's amazing is that so many of those core concepts that Feynman was wrestling with back in the 80s
Mm-hmm.
have become absolutely essential to modern AI and machine learning,
Yeah.
like the shift towards data-driven approaches.
Right.
I think Feynman would have loved that.
Yeah.
I mean, with his scientific background.
Right.
That's just how he thought about
Yeah.
things.
Evidence-based.
Exactly.
Yeah.
And the source lists all these neural network architectures and learning methods. Things like convolutional neural networks, recurrent networks, attention mechanisms
Yeah.
that have completely revolutionized the field.
It's like he saw the seeds of this revolution being planted.
Yeah. He was ahead of his time in a lot of ways.
And the success of these methods has been just transformative.
It has.
The source gives some examples like AlexNet in computer vision,
Uh-huh.
AlphaGo in game playing, and GPT-2 in natural language processing.
Those are just a few examples
Yeah.
of the impact that neural networks have had.
Yeah.
They've gone from this niche research area
Mm-hmm.
to being these indispensable tools across countless applications.
Right.
And they're doing things that we used to think were like science fiction.
Yeah.
And the source really emphasizes how much both the tech industry and the core sciences rely on these machine learning techniques now.
It's everywhere.
It really is.
So what do you think Feynman would have thought about all this progress?
I mean, it's hard to say for sure,
Yeah.
but based on what we know about him, I think he would have been really comfortable with that data-driven nature of the field
Okay.
and the emphasis on experimental validation.
Right. He was a scientist at heart.
Absolutely. He always valued evidence above all else.
But he was also a healthy skeptic.
Oh, yeah.
He didn't just take things at face value.
He was wary of what he called too much happy talk in science.
Right.
And I think he would have applied that same skepticism to some of the issues in the AML community today.
Okay, like what?
Things like over-reliance on benchmark data sets
Okay.
or selective reporting of results.
Right, just highlighting the good stuff.
Exactly.
Yeah.
And that's something important for everyone to keep in mind.
Right.
It's not all sunshine and roses.
On the other hand, I bet he would have been genuinely excited by some of the clear successes,
Right, yeah, definitely.
like transfer learning,
Mm-hmm.
which echoes his earlier ideas about a learning machine that could master skills sequentially.
Yeah, like a child. That ability of networks to learn from one task and apply that knowledge to a totally different but related task,
Yeah.
I think that would have resonated with him.
What about his view of the equations themselves?
I think he might have had a mixed view there.
Okay.
I mean, he would have appreciated the mathematical framework,
Right.
but maybe found them lacking that deep conceptual meaning that he sought in physics.
Right.
Like maybe he would felt they were kind of neat but not deep enough.
Yeah, I could see that.
And I don't think he would have been too bothered by the kind of messiness of some AI solutions.
Right.
You know, that collection of ad hoc techniques that sometimes lead to breakthroughs.
As long as it worked.
Yeah, as long as it worked.
That was Feynman.
Absolutely.
Very pragmatic.
But the source does suggest that he might have been particularly intrigued by network architectures that have deeper connections to physics.
Okay, like what?
Things like manifold learning.
Okay.
And maybe those efforts to bridge the gap between artificial and biological neural networks.
Right, to understand how the brain actually works.
Yeah, those are areas you might want to keep an eye on.
Yeah, for sure. And what about the application of AI and machine learning within the sciences?
Oh, I think that would have been a huge area of interest for him.
Right up his alley.
Given his passion for physics,
Yeah.
this whole field of physics-informed machine learning,
Okay.
where you're incorporating scientific principles into the design of AI models,
Yeah.
I think that would really captivated Feynman.
Yeah, the source even suggests that this might be the single most exciting development in AML from his perspective.
It's hard to disagree.
It's really fascinating to imagine the new ideas he might have come up with
Yeah,
if he had access to these powerful tools
absolutely.
and was tackling these complex challenges.
I mean, he would brought his unique blend of intuition, creativity, and deep physical insight.
Right.
Who knows what he would have discovered?
So let's talk about how AI and machine learning are actually being applied in computational science right now.
Okay, so we're seeing this huge trend of using neural networks to solve problems across a whole range of scientific scales.
Okay.
Like in quantum mechanics.
Yeah.
You've got specialized architectures like Ferminet
Okay.
that are being used to approximate solutions to the Schrödinger equation,
Okay.
which is notoriously difficult to solve.
Especially for systems with many electrons.
Yeah, exactly.
So AI is helping us understand the behavior of matter at the most fundamental levels.
It is.
Wow.
And it's not just quantum mechanics.
Okay.
In molecular dynamics, machine learning is speeding up simulations
Okay.
and even learning those potential energy functions
Right.
that govern how atoms interact.
Okay.
And that leads to these multi-scale models.
Okay, so we can connect the microscopic to the macroscopic.
Exactly.
And it doesn't stop there.
No.
Right.
You've got people using neural networks to model complex fluid flows
Okay.
and other continuous phenomena.
Yeah.
They're using them to directly solve or even learn partial differential equations. And there's also some very promising work using machine learning for model reduction,
Okay.
which is all about simplifying complex systems while still capturing their essential behavior.
So AI and ML are becoming essential tools for scientific discovery
Absolutely.
across all these different disciplines.
From analyzing huge amounts of experimental data
Yeah.
to informing the development of new theories.
Mm-hmm.
Machine learning is changing how science is done.
The source talks about this hierarchical approach,
Yeah.
tackling problems across different scales of complexity.
I think that would really resonated with Feynman,
Yeah.
that interconnectedness of knowledge.
That was how he saw the world.
Exactly.
Okay. The last part of our discussion in the source focuses on this idea of a potential mathematical synthesis
Okay.
and even a possible return to some aspects of symbolic AI.
Interesting.
Yeah. Given how dominant these neural network approaches are right now,
Right.
that's kind of an unexpected twist.
Yeah, but it makes sense when you think about it.
Okay, how so?
Well, there's this growing need for more explainable AI models.
Right. Systems where we can understand the reasoning.
Exactly. And that's one of the motivations for maybe bringing back some of those symbolic approaches.
Okay.
And you got to remember that even most machine learning methods
Mm-hmm.
are ultimately defined by equations,
Right.
which are symbolic.
Okay.
So there's always been this connection there.
And there's been a lot of progress in symbolic computing areas like computer algebra systems
Right.
and automated theorem proving.
Absolutely.
So the idea is to combine those strengths
Right.
to create something even more powerful.
Exactly.
The source mentions some recent work integrating machine learning with computer algebra
Yeah.
for things like symbolic integration
Right.
and even using ML to improve theorem provers.
And on the flip side,
Yeah.
we can use those formal methods from theorem proving
Mm-hmm.
to verify the theory behind ML
Okay.
and improve code generation.
So it's like a two-way street.
Exactly.
The source even quotes Feynman. Oh, yeah. About sometimes knowing more than you can prove.
I love that quote.
Yeah, it suggests that a purely axiomatic approach might not be enough.
Right.
Yeah.
Sometimes intuition and experience play a role.
Exactly.
And the source also mentions symbolic regression,
Okay.
where AI is used to rediscover physics formulas from data.
Oh,
So
wow.
we're seeing these hints of a future
Yeah.
where symbolic and numerical AI are working together,
Yeah.
especially in computational science.
That's a very cool vision.
It is.
So to sum it all up, it seems like Feynman, even back then,
Mm-hmm.
had this incredibly forward-thinking perspective
He did.
on the potential of machine learning.
He saw something that a lot of people missed.
Yeah.
His focus on fundamental principles
Mm-hmm.
and his just boundless curiosity
Yeah.
would made him a major figure in this field if you were still around.
Yeah, what's really striking to me is how his early intuition about symbolic AI's limitations and the power of learning from data
Mm-hmm.
have been so thoroughly validated by all the progress we've seen.
It's amazing to see how those ideas have played out.
And it makes you wonder what other seemingly unrelated fields
Yeah.
might hold the key to future breakthroughs.
Right.
Not just in AI,
Yeah.
but in all areas of knowledge.
It's a reminder to keep an open mind
Absolutely.
and explore those unexpected connections.
That's what Feynman was all about.
Exactly.
So thanks for joining us on this deep dive into Feynman's early thoughts on AI.
My pleasure.
It's been a fascinating journey.
It has.
For your continued exploration, think about how seemingly disparate fields might intersect
Yeah.
to spark those next big scientific leaps.
That's where the real excitement